particularly as you know you're going to be addressed by the real unknown Turing. I have to say I'm quite proud of that. As built, I think rather than spending a lot of time talking about what happened at Bletchley Park, which is probably a story that you all know rather well and probably rather better than I do, I thought what we might do is just home in on machinery, because for some reason I thought that might be of interest to some of you. And I thought we might also look at some of the things that he did with the machines, which are perhaps, as suggested, sort of rather less well known. And so perhaps what we ought to do is just sort of begin at the beginning, though, which is this paper, which I'm sure you've all read. There are exam papers to test your knowledge at the back, which you can fill out with the approval sheet at the end. This is all quite interesting because this is the work stimulated by the man on the left, who you will recognise as Max Newman, the Cambridge maths don, who gave the talk on the fundamentals of mathematics, well, in fact a series of lectures for Cambridge, and both Cambridge and Oxford in the pre-Second World War period were a bit peculiar about master's degrees and so forth, because of course all Oxbridge graduates get a master's degree automatically. So they didn't really have proper master's courses, so they sort of tacked on an extra year for bright students after they're essentially completing their bachelor's degrees. And so that's what Alan Turing was doing. It's effectively a master's course, which was sort of like part 3 or sort of additional supplementary lectures. And so Max Newman was giving these postgraduate, sort of quasi-undergraduate type of lectures on fundamentals of mathematics. And they were looking at the problems like the Scheidung's problem, the question whether there is some way that you can tell ahead of time whether any particular theorem is going to be provable or not. How do you go about that? And Newman described this problem in terms of a mechanical process. Is there a mechanical process by which you could work out whether any given theorem is provable or not? And Alan Turing sitting there in these lectures, and there's probably only a dozen students in these lectures, is sitting there and thinking, mechanical process. And he takes this idea of mechanical process away, and he comes up with this proof of the Scheidung's problem. In fact, it's a disproof of the Scheidung's problem, and also this idea of a universal computing machine. Now, you have all worked with universal computing machines for all your professional lives. I want you to now go back to your kitchens. Okay? Now, when you go into the kitchen, you have various pieces of machinery, and they're all quite useful. You have a kettle that's used for boiling water. You may have a mixing machine that's used for mixing things. You may have a dishwasher that clears up the mess afterwards. You may have a cooker that you can sort of heat things in. But none of these are universal machines. They're all single-purpose machines. And all calculating machinery, with the possible exception of punch card machines, which I don't want to go into because you know far more about that than I do. Basically, machinery pre-World War II was single-purpose machinery. The idea of a universal machine that could be reconditioned to do multiple tasks. Quite stunning idea. It's obviously theoretical. It's totally impractical. It cannot be done. So it's clearly a theoretical device to solve a theoretical problem in the rules governing mathematics. It's not really ever intended to be practical. Or was it? Because actually what this leads Alan Turing to do is to start thinking about the instruction tables that you need to create to make his universal computing machine do different tasks. He starts thinking about algorithms. And I want to introduce you to this lady. You've all heard about Alan Turing. Most of you seen The Imitation Game. You've probably most of you read Andrew Hodges' biography of Alan Turing. You will have a clear picture from either of those of Alan Turing's sort of schoolboy relationship, so you pick a neutral word, with this chap Christopher Morcom, who was another student at Sherborne School, and how this sort of like governed the emotional development of Alan Turing and indeed stayed with him for the whole of his life. Actually, I think the story is slightly more interesting than that. The real relationship is not between Alan Turing and Christopher Morcom, which lasted at most 15 months. It's a relationship between Alan Turing and Christopher Morcom's mother, which lasted over 10 years. And she's a very interesting character. First of all, I can say this safely to a British audience. We all know, because we're Brits, that this business about the light bulb and Edison is an American myth. We know that the light bulb was invented by Sir Joseph Swan, this lady's father. And not only is she descended from a very bright line of scientists, she's encouraging her sons to go off and experiment in a laboratory in their fairly extensive set of buildings and outhouses in Bromsgrove. So very unlike my grandparents, who wouldn't really cope with the idea of anything messy and dangerous going on in their property. But she's also a sculptress. She's very hands-on. She's a very interesting kind of person. Rather, she's effectively, for Alan, a sort of mother substitute, but she can also talk to him in his own language. And so, shortly after writing his paper on computable numbers, he's talking to Mrs. Morcom about algorithms. In particular, he's talking about algorithms for playing games. So he's got the game of Go, he's giving her a set of rules for Go. But he's thinking the whole time, which you can see on the slide here, he's thinking the whole time about programming for theoretical machines that don't exist, but he's taking the concept outside the theoretical mathematical space. This all, and we can talk about why this might be, but I think this sort of stems from a very sort of hands-on practical approach that was instilled into him at his prep school. But let's not get bogged down in that. I want to get onto this, which is the blueprint. This is not an Alan Turing drawing. Alan Turing was incapable of producing a beautiful engineering drawing like that. But this is a drawing of a machine that he invented, which was all about solving a problem about the spacing out of prime numbers. Okay, you think about it. Prime numbers they aren't evenly spaced across the numerical spectrum. They cluster in various ways. And so the question is, can you predict the ways that the prime numbers cluster through the Riemann zeta function? Don't ask me to do the Riemann zeta function for you. But anyway, so he was trying to find a mechanical, this is an analog approach to a single-purpose machine, trying to see if he could actually find the solutions to the Riemann zeta function, and it involved cutting brass gear wheels with numbers of teeth that were prime numbers, and you fit them together to have approximations of these calculations. This is going on 1937, 1938, with brass gear wheels strewn all over the floor and the table in his rooms at King's College, Cambridge. He's actually making machines now. He's not making a universal machine, but he's actually wanting to get hands-on and trying to do it himself, or with some help, because milling these brass wheels is non-trivial, and he needs some help in the lab. But this is quite interesting. He's not just a theoretical mathematician, he is also wanting to get his hands dirty and do some real engineering and make machines. Obviously this puts him in an absolutely perfect position when Bletchley Park needs effectively a mechanical solution for cracking the Enigma problem, finding the daily settings on the Enigma machine, and he comes up with his design for a bomb which will crank through all 17,576, thank you John Harper for telling me the number, and cranking through all the number of permutations on the three wheels on an Enigma to effectively try and eliminate the vast majority of the improbable permutations. This is a very interesting machine. we're beginning to get a bit closer to a computing machine with this. No, it's not a computer. No, it's not a computer. So you can save the squishy tomatoes for later. But there are some interesting aspects of this machine which I think are sort of casting light into the future. First of all, it's a digital machine. It's giving you a yes or no answer. It's not an analog machine. It's not providing an approximation to anything. It's actually giving you a digital yes or no answer. Some of the yeses are wrong, but it is digital. It's also programmable. Okay, it's single purpose. It's only got one purpose, which is to try and find the settings on an Enigma machine. But it's programmable. You reprogram it, you rewire it around the back for every day's new problem. So it's got some characteristics in common with a programmable computer. Now, of course, those of you who've seen The Imitation Game and believed it will know as incontrovertible fact that Alan Turing sweated alone in some ghastly hut in Bletchley Park for the duration of the war to try and solve this terrible Enigma problem, and eventually managed, in the nick of time, with 10 seconds to go before the Normandy landings, managed to make the bomb actually work for the first time. And, oh, thank God for that. And suddenly the Battle of the Atlantic was won, and D-Day landings happened successfully, and thank goodness for that. Actually, the truth of the matter is rather more interesting, I think, because the design for the bomb was actually ready for discussion with the engineers by Christmas 1939. And the prototype bomb was delivered in the spring of 1940. It didn't work. Gordon Welshman's addition to it was thought of in the early part of 1940, added into the design, and by essentially the time of the Battle of Britain, they actually had functional bombs working at Bletchley Park which were able to do the job they were supposed to, that is, find settings in a more or less real-time basis to provide some intelligence. So that's as early as autumn 1940. So you then have to ask yourself, well, what did Alan Turing spend the next 5 years doing? Because his greatest wartime achievement, if you think his greatest wartime achievement was this thing, so what did he then spend his time doing? Well, clearly the Enigma wasn't the only problem. Naval Enigma was a much tougher nut to crack, and so that required a serious amount of brain power. But essentially by 1942, his role as a cryptanalyst has receded somewhat. Bletchley Park's become more of a factory, and we'll have a look at that in a second. But Alan Turing sent off to the United States this rather curious looking building. Actually, this rather curious looking building is where Bell Labs, so that's the equivalent in the US of the Post Office research place at Dollis Hill. It's where Bell Labs were building their own variety of the bomb. And so he was sent to go and check out their work. But he was sent out to do some other things as well. And these are really give a bit of a clue as to what he was going to spend the rest of the war doing. First of all, he was sent out to check up on a new teleprinter encryption device, which was being developed in the US by the Canadians, actually, working with the Brits, but out of a secret place in New York. So he was being sent to check out whether this teleprinter encryption methodology was going to be secure. He was also sent to look at another thing going on in this Bell Labs building, which was the development by the Americans of a speech encryption device, which was designed to help things like Roosevelt and Churchill have their transatlantic radio telephone calls without being eavesdropped on by the Germans. Incidentally, the Germans had been listening to Churchill's telephone calls from about 1940 onwards, so this was a real security issue. So he was sent basically to go out and vet the quality of Allied communication security. This is a different role from cryptanalysis. This is basically being a security guy. He's changed sides in the encryption debate. Right, now you're all puzzled about this train running through this building, so I've got to tell you about the train running through the building. Okay, you can still go and visit this. In New York, there is a high-level railway line that they put together at the beginning of the last century to run from the meatpacking district down to various other parts of Manhattan. And they, because the city was obviously very well developed at that time, they couldn't run trains at street level, so they put it on an elevated section. Most of the elevated section has now been turned into a park, which you can walk along, and but this particular building isn't part of the park. It's about 200 metres south of the park, but the building looks exactly as it did in 1942, roughly, when this photo was taken. There aren't trains running through it anymore, but you can go and see it. It's nice shishi apartments, but it's still there. And the photographs I took in November last year were absolutely the same as this. It's really, really very interesting. Okay, and then there's this rather peculiar thing on the right-hand side of the slide, which again John Harper will probably tell you far more about than I can. This is Delila. I'm sure he comes back from his experience of looking at this machine, the speech encryption machine that the Americans have been developing. It weighed 40 tons, and it took up 50 racks of electrical and mechanical equipment. When he signed off on it, so it was okay. So they decided to bring one to the UK. There was no room in Whitehall that was big enough on the ground floor to be able to install this piece of equipment. And because it weighed 40 tons, they couldn't send it upstairs anywhere. So the only available place for it was Selfridge's department store basement. So that's where the secret phone calls had to be processed. It's all quite interesting. I'm showing this is complete nonsense. Why do we need 40 tons of kit to encrypt a phone call? So he designs a machine, this Delila thing, which is about the size of an Enigma machine. You know, it's portable. And he says, look, this problem about speech encryption, it's much more significant than just Roosevelt and Churchill having their private phone calls. It's about tank-to-tank communication, and it's about plane-to-ground communication, which is currently going on in plain speech at the minute, and it's being listened to. Let's cure that problem. He managed to get his design ready in time for D-Day, and the prototype was up and running by the end of the war, but for whatever reason, I think American technology dominated, and this huge, great 40-ton thing, which obviously was never going to be put in a tank or an aircraft, prevailed and was in use for at least 10 years after the war. And Delila, I think, just went to rot. But I think this is quite interesting because, again, you've got Alan Turing. He's not just doing the theory. He wants to roll up his sleeves. He wants to pick up a soldering iron. He then needs to be told by somebody who actually knows what they're doing, and like, get the hell out of the way, Alan. We know how to do this, and thanks for your help. But you stand over there and watch. But at least he wants to get on with this stuff. He's interested in the machinery as well as the theoretical design concept. I'll probably put these slides in the wrong order, but this is all going on because effectively by this stage, this is Bletchley Park in 1943. In fact, this is a Bletchley Park outstation in the photograph rather than Bletchley Park itself. You get the sense from the map that Bletchley Park's turned into an industrial complex. It's a code-breaking factory. It's not really the place for Donish amateurs anymore. It needs to be run like a military operation, and it is. And that's why this wren who is sitting by her bomb there looks so incredibly bored, because factory workers with dull jobs, they get bored. And that's my favourite World War II Bletchley Park photograph because of the expression on her face. I don't know whether she's still alive. Somebody told me the other day that she was, so I hope she's not insulted by me saying that. There was some interesting stuff going on there still, though. And again, Max Newman comes back into the picture. He's a late recruit at Bletchley Park for interesting reasons, but Max Newman concluded that the breaking of the Lorentz cipher, the teleprinter codes being used by the Germans could helpfully be mechanized, and he was put by Commander Travis in charge of a machine section, which would eventually lead to the building of this thing, which of course you all recognise as being Colossus. But interestingly, at around about the same time, Travis set up a sort of a consulting group, if you like, of people we now recognise to be the great and the good from Bletchley Park, chaired by Gordon Welshman, with Max Newman sitting on it, and also with Alan Turing sitting on it, which is a look at all mechanical problems that Bletchley Park was confronting. So there was not just things like the building of Colossus, but it was also about things like the availability of punch card equipment, and how to prioritise the use of different machines and development of different machines, four-rotor bombs, you name it. All mechanical problems would go through this committee to be looked at. And I think this is quite significant because I know that computer historians for years and years wanted Alan Turing to have been absolutely the key mover behind the Colossus, and despite their best efforts, it's been impossible to prove anything other than a very tenuous link between Alan Turing and the development of Colossus. But Alan Turing was clearly involved, partly as a consultant through this committee chaired by Gordon Welshman, and partly just because there were people like Newman around who wanted to consult with him and make sure that they got his ideas on board. And that meant that he was aware of what was going on. He was aware of the uses to which he was being put. He was very friendly with Tommy Flowers, and so I think it's a fairly collegiate kind of atmosphere you've got going on there. Even though it's turned into this intelligence factory, the cutting edge on the technology is still involving these people and their brains. That, I think, then sets up Alan Turing rather well for his post-war work. As we all know, what he did immediately after the war was come up with his blueprint for the automatic computing engine, the first universal electronic programmable computer that was going to be built in Britain. There was this big raging policy debate about whether Britain would need one computer or whether it might actually need two. Sir Charles Darwin, sitting down there in the bottom left-hand corner of the slide, the head of the National Physical Laboratory and the prime mover, and Sir Charles gets a bad press because he made some sniffy remarks about Alan Turing, who wasn't a particularly good civil servant, it has to be said. But frankly, he did recognise Alan's brilliance. There were some impracticalities in Alan's blueprint. The problem was that the automatic computing engine was using mercury delay lines as its memory. I'm not going to tell you how they work because you know it better than I do. There's a picture of one up there. Various other exciting memory devices from the late 1940s. The winner, of course, was the Williams tube at the top, but the ACE design was using mercury delay lines. And Alan's idea, which I think is probably a bad idea, it's very dangerous for me, the unnamed Turing, to say that any of my uncle's ideas were bad ones, but this one I believe to have been a bad one. He thought that elegance in programming was the answer to computer efficiency, and it was all driven by the technical deficiencies of the delay line. You had to make sure that as the piece of data popped out at the end of the delay line, which might be this year or it might be the week after, your program was just ready to capture that piece of data and then process it immediately. So that meant that your program had to be designed in a way that logistics suppliers these days talk about just-in-time delivery. This was just-in-time programming. If you had a Williams tube, you didn't need to think about it that way. You could program in the most haphazard and disorganized way that you liked. The technology would sort you out. Alan his mathematician in him just was offended by that. You needed elegance in your programming, and it was worth spending the time on the program and not worrying about technology. Of course, the Cambridge computer scientists said, you've got this all inside out. The technology will improve, it will improve faster than you can think. And actually, we don't need to fuss about getting the program right. We can rely on the technology to sort us out. Let's get on with the job. And it's very interesting. The thing you can see on the right-hand side is Tilly will kill me for this because I've stolen a Science Museum photograph here without accrediting it on the slide, so I'm going to accredit it orally. This photograph of the pilot ACE is a Science Museum photograph. The ACE was just an absolute monster. It took years and years to develop, and so they started off with this proof of concept thing, and frankly, again, this offended against Alan Turing's purest instincts, drove him away essentially from the NPL for a while, where he went to do his work on artificial intelligence at Cambridge. And this is all very interesting. Why have a proof of concept? Let's just get on and build the whole thing. No, that's not how it's going to work. A parenthesis. At this point, Alan Turing takes up running. This is a very weird thing to do. This guy's 37 years old at this point, and he's taken up marathon running, and he's actually really rather good at it. The splendid people at the Wartime Athletics Club have still got records going back to the immediate post-war period, so they've been able to do things like find the programs for some of the athletics meetings that were taking place in the lead up to the 1948 Olympics, and we've got pictures of Alan Turing running races and programs with him in, and we know what his times were and that kind of thing. And it turns out he was actually he was best at 3 miles rather than a marathon, but only narrowly missed selection for the 1948 British marathon team. So it's all very interesting. Why is he doing this suddenly in his sort of late 30s? He's picked up this kind of thing. Anyway, back to the real business in hand. This is ACE. This is a picture again from the Science Museum archives. There's some very, very interesting stuff in the Science Museum archives in Swindon. Some previously unpublished pictures of ACE in various stages of its development. These racks you can see, you've probably seen the pictures of ACE when it's completed, with lots of sort of white-coated, earnest-looking people running around sort of tending to it. But when it's half built, it's really very interesting. There's pictures from probably about 1956, around about then. They're not dated, so you have to guess a little bit. But the thing wasn't up and running until the late 50s, long after Alan Turing had died. So waiting for the real ACE was not a good plan. Instead, he's rescued by Max Newman, and he's sent off to Manchester, where they've got a proof of concept machine running. We mustn't call it that because that will offend Alan Turing. He wants to have a proper computer to work on. But at least they've got a computer and it's actually working. It's in the Royal Society Computing Laboratory. Sounds great. It's actually the basement of the building where Rutherford split the atom. Professor Williams, who invented the Williams tube, wrote about it in the 1970s, and he said that the architectural style was Victorian late lavatorial. It's sort of like brown glazed brick, and I've been allowed to go into that building, and it's still quite interesting, and they've got lots of the original fittings and furniture in there because it's a bit radioactive and they can't teach students in there at the minute. So the computer scientists were basically given the magnetism room in the basement of this building to do their work, and this is what they came up with. It was called by the Illustrated London News a marvel of our time. Well, I think it's marvellous, but it does look a bit ropey. I mean, look at it. It's really quite terrible. It's made out of leftovers from Colossus that Max Newman had managed to convince the GCHQ to let him basically have the bits and pieces. There were all these tubes lying around, basically valuable bits of kits that weren't going to be used. So he took 2 colossi and a 7-ton truck full of bits and pieces up to Manchester, and with their soldering iron they built this. It was a 1024-bit memory. You couldn't really do a lot with it, but you could solve a 300-year-old sum. You probably can't read that. The mechanical brain. This is the Times from June 11th, 1949. The mechanical brain. Answer found to 300-year-old sum. What on earth are they talking about? Okay, Mersenne primes, 2 to the power of n minus 1. Sometimes it's a prime number. Mersenne had come up with a list of numbers n, where he said this is a prime and this is not, up to about 250 something or other. But if you work these out, even with a mechanical adding machine, to do the maths, do the arithmetic necessary to work out whether 2 to the power of n minus 1 is a prime number or not, it's a labour of love. It will take hours and hours. And so Max Newman, who really is an incredibly clever guy, says, I've got a computer with a memory of 1024 bits, but it just occurs to me that 2 to the power of n minus 1 is a number that looks like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So I can get the computer to test whether these are prime or not. So the first program they were running on the Manchester Baby, the marvel of our time, was to test Mersenne's list of primes. And I think they said he made one mistake in his list of primes up to 200, n equals 257 or something like that. But it was great. The Times thought this was great. They wanted to publish it. They've got an electronic brain going in Manchester. It's like rockets to the moon, isn't it? They had reckoned without Sir Geoffrey Jefferson, FRS, a gentleman on the left here, who was the professor of neurology. Sir Geoffrey Jefferson also gets a bad press, and it's not fair because he was really. Everybody says that when you're a kid, you all get told that the brainiest person in the country is not a computer scientist; he's a brain surgeon. Sir Geoffrey Jefferson was a brain surgeon, and through 2 world wars, he'd actually been patching people up who'd got terrible, terrible head wounds and recreating their lives for them. So he's a very, very impressive individual, very, very good in his field. And to honour his work, he'd been awarded the Lister Prize in 1949. It's awarded only every 2 years to a very distinguished medical scientist. And the winner of the Lister Prize is expected to give an oration. They don't just give a speech, they give an oration. And so Geoffrey, knowing what's going on up the road in Manchester, he's based in Manchester as well, knows what's going on up the road, says, they're doing this terrible thing. They're doing something that's philosophically and morally shocking. They're trying to imitate in mechanical form the processes of human brain, and I think that's immoral and wrong. And so his Lister oration is devoted to the question whether it is even a proper question to ask, can machines think? And he goes on and talks about computers doing things that only humans could do, like writing sonnets. Oh dear, we get a little bit of a problem here, because the Times has sent a reporter to the Lister oration. And they're very interested in hearing about this mechanical brain, hence the piece on the 300-year-old son. They phone up some bloke in the computing laboratory in Manchester who apparently rejoices in the name of Mr. A.W. Turing. Oh dear. And Mr. Turing then spouts a whole load of stuff about sonnets, and then he says, well, of course the computer, this computer maybe not, but in years to come, of course computers will be able to write sonnets, but I think that a sonnet written by one machine will be better appreciated by another machine. he nearly got fired. So Newman has to pick up the pieces and sort of say, oh no, it's really, really boring what we're doing. We're not trying to sort of, make machinery imitate life, and we're doing this really boring thing about prime numbers. So he's sort of like having to write apologetic letters, and the church gets involved, and you know it. Actually, the reality of programming a Manchester machine was really rather more prosaic. What happened was, of course, this was a proof of concept machine, but they proved the concept. And so they sent off, in partnership with a firm called Ferranti in Manchester, they came up with a rather more splendid looking computer that really doesn't look like a marvel of its time, because all the parts are hidden behind sort of nice metal cabinets, and you even get a sort of an attractive lady to sort of model the sort of computer operation for you for the brochure. So this all looks very clean and not at all like the magnetism room at the bottom of the Rutherford building. And the actual process of programming is still really, frankly, a complete pain. This little excerpt from a program was taken from the Manchester University archives, and you can see Alan Turing's handwriting on it on the right-hand side of the slide. They said, "How did this happen? Something's gone wrong." And he's sitting there at 3 o'clock in the morning, and the machine's crashed, and he doesn't. He's trying to pick out the reasons why in some horrendous sort of 32-character code that's got punctuation symbols and so forth. And of course, it's arithmetic's ran the wrong way with the least significant digit on the left and all this kind of stuff. So I mean, it's not intuitive, and it's a complete nightmare. What a surprise to discover that the programming manual for the Manchester Mark I computer was rewritten by people to do it more sensibly, like have the numbers the right way around, and actually be more usable. He was very sniffy about that, as you can imagine. We're all a bit like that, actually, aren't we? We had to learn things the hard way, and then when they produce something like Windows that's supposed to make a nice user interface, we get a bit grumpy about that, because why shouldn't the youngsters have to do it the hard way like we did? I can just sort of, but he wasn't really being any different from the rest of us on all that stuff. But, I can't think of a good reason, but I know it's not right. What is more interesting is what he was actually doing. Because yes, he was doing the programming manuals, or after a bit, because other people could do it better, he wasn't. What he was really doing, what he'd really gone to Manchester to do, was to use the computer, not to design it and not to program it, but actually to use it. And again, Max Newman is a very important influence here, because Alan Turing does what looks like a quantum leap into another field, which is developmental biology. And I've been asking myself for a number of years, why would Alan Turing suddenly leap into a completely new discipline like this? But I think the clues are here, actually. Partly it's about using the computer, but it's partly because Max Newman is a topologist. Max Newman isn't really, I mean, he may be most famous these days for influencing Alan Turing's life and for his work on Colossus, but actually for the whole of his professional mathematical life, he was a topologist. He wrote the textbook on topology. And so he's actually constantly talking to people who would listen about shape and form and how you sort of bend things and what happens if you stretch things. And this is the problem of developmental biology. Alan Turing reckons that you can explain things like this problem. A horse is not a spherically symmetrical object, yet it starts out life in embryonic form, shaped like a tennis ball. How does the tennis ball know to stick a head at one end, 4 legs and not 6? How to make the legs go at the corners and not sort of randomly distributed? How does it know about that? And he thinks you can explain this through the diffusion of chemicals at different rates through the spherical embryo. And he thinks you can explain a lot of things about animal and plant form through this diffusion model. The only problem with the diffusion model is that it uses horrendously difficult partial differential equations that you absolutely cannot solve using a pre-war calculating machine. But you probably can get the Manchester Mark I to have a go at them for you. And so he comes up with this paper in 1951 on explaining his theory, the chemical basis of morphogenesis, and he is able to model things like the patterns of a Frisian cow coat, for example, which is this background to this slide is taken from his paper. That's real. That's a real diagram based on his equations. Now, if I can get the technology to work here, I may be able to show you a model that's been done by a German professor called Felix Wojcel. Yes, it looks as if it's coming up. This is a demo of Alan Turing's equations. We just need a minute, I think, for Chrome to work. Do I need to? Here we go. Tiny mashup. Looks rather black, doesn't it? If I try refresh, and then we'll see what happens. It was working fine before we started. Never mind. Where do I find my presentation again? Kevin, I'm going to draw over here. It's a big P. I'm sorry that didn't work, but never mind. Oh. Come on. There we are. Okay, well, I'm sorry about that, but there's a when you get home, take Felix Wojcel's name and stick it in your browser, and then you'll be able to run a little simulation of Alan Turing's equations. What you'll see is the screen starts off completely grey, and then suddenly dots of colour emerge. You can actually move your mouse around and swirl it around to get different patterns coming out, but you can actually see a pattern emerging, and it's just as the colours representing the different chemicals diffuse across the mass, and peaks and troughs will appear, and that will explain various things. Alan is using the computer to create contour maps. It's very interesting. They had a conference in 1952 at Manchester University. Well, computer labs were all having conferences at the time, and a lot of it's technical and about things like memory and programming techniques and so forth, but some of it's about apps. And they had James Kendrick, for example, came to Manchester to talk about how he was going to use the Cambridge computer to create contour maps to uncover the structure of biological molecules, which, as we all know, led to things like the structure of things like vitamin A and eventually DNA. DNA actually put the kibosh on Alan Turing's developmental biological work, because everybody, including me, got so obsessed with the idea of DNA as being the explanation of all things biological that for probably 40 years nobody could get a research grant unless they had the word DNA in it somewhere. And so anything that was sort of mathematical or chemically based that didn't use DNA as the chemical they were interested in just didn't get anywhere. So his work got eclipsed. But I think this is quite interesting, because this again comes from the Manchester archive, and this is an example of a computer readouts that Alan Turing has painstakingly copied out onto squared paper. So you can see lots of two-digit numbers there, all in this terrible 32-character code, at least lesser significant digits at the left, and he's drawn a heat map on top of it, or an intensity map, to show where the larger numbers are, and so he's actually producing a contour map, and that's the kind of thing that was being used to create the Frisian cannon picture. But that wasn't all. There was the work on plants. These diagrams take a bit of explaining. Sorry, they're in black and white. The originals are in colour, but the top diagram, you have to imagine that what you've taken is the stem of a plant and you've slit it with a razor blade down the back and then unpeeled it to make a flat piece of paper, and the dots are where the buds or the branches or the leaf joints are. And you can see that they're in spiral patterns. And so the question is, can you explain this, this patterning through the chemical diffusion model and the equations that he got? And you also got his work on radial area, which was the last research project that was being done at the time of Alan Turing's death by Bernard Richards, who's still alive. Bernard's own career is very interesting. He's having started out as a pure mathematician and then ending up as a professor of medicine. His postgraduate research project was working on these strange beasts, which are radiolaria. They're dredged up from the sludge at the bottom of the Atlantic Ocean. They're microscopic creatures, but the patterning of the spines on these things, Bernard was able to use Alan Turing's equation to model and predict the positions of these spines on these rather extraordinary things. So they're great. The pages and pages of them from the Atlantic survey of the 1890s. Then we get to the end of Alan Turing's life. I've put this slide up partly to amuse you and partly to interest you. This is Alan Turing's house as it is today. Apparently busloads of Chinese tourists go up the roads there, and it's a sort of a busy, it's like sort of posh suburbia in Manchester, so it's a busy, quite narrow road, and having a busload of Chinese turning up with cameras and spilling over the front garden must be incredibly annoying. As you can see, it's a semi-detached house, so both neighbours have a problem with this. I didn't bring a busload, but I was kind of like doing the same thing, turning up with my own camera, saying, do you all mind if I take a picture of my uncle's house? There we are, so there it is. And I put the estate agent's plans, because it changed hands fairly recently. The estate agent's plans, which it's been developed quite a lot since 1954. It's got a gym and various other things in it which weren't there in Alan's day. But I thought you might be interested in the room layout on the first floor. The front room is the bedroom, and the room behind it is Alan Turing's laboratory. And although this isn't anything other than very weak evidence, it seems to me that if you're making a solution of cyanide using something plugged in, like barbers used to, you plug something into the electricity slot where the light bulb is supposed to go. He's using something like that to cook up his homemade cyanide in the laboratory. The idea that it was an accident, that he had somehow sort of dipped his finger into this by mistake and then conveniently gone into the bedroom and died there, seems to me to be very difficult to support once you see the room layout. There's other reasons why I don't go along with the accident theory, but I thought you might just find that quite interesting. Right, people are bursting with questions, so it's clearly time for me to stop. And thank you very much for your patience. As I say, I will be delighted to take questions. I think there will be a roving mic or two.
Well, thank you very much indeed for such an into and different angled talk on Alan Turing. So, thank you very much.
With the questions, I'm here under duty to tell you about something nothing to do with Alan Turing, except this is part of his legacy. The Turing Trust. Just want to mention this. My son has, some of you who have been to the lectures of the Royal Institution will know about this already, but my son has set up this charity called the Turing Trust. We try and recycle old computers that have gone past their useful modern life in the UK, but can still be reprofiled and used to put into underprivileged schools in Africa. So if you're interested in that project, please pick up a leaflet. There's a handful here at the front. If you know of anybody who's got lots of preferably identically configured computers that we can easily reprofile. It's not quite like Bletchley Park 1942 factory operation, but it's getting close to that now. So we've got a lot of success, but I thought you guys might be interested. Thank you. All right, questions?
Thank you for an illuminating talk. Dave Michelle had the privilege of being hosted with other BCS members at the House of Lords last night, and it was put forward that to die accidentally, as you've just described, to have an inquiry exactly 2 days later, and to be cremated exactly 2 days after that. It seems odd that we're at the time of the Cold War, just before Suez, and it seems even odder when you consider the US had given us data that Neumann clearly had processed in the US that would have used a Turing machine that obviously wasn't built by Allen. The data being the equivalent of what the nuclear fallout from the Bikini Atoll would have been to declare it, and the fact that Churchill made a decision exactly a week later to build the UK's H-bomb. I don't know if it's an accident or not, it's just coincidence, I'm sure. But thank you for expressing that at all. And one of you have an opinion on that?
Thank you. Yeah, I mean, it is true that the inquest took place less than 48 hours after Alan Turing had taken his life, or at least 48 hours after his body had been found. Now, I haven't done any research to know whether that speed was unusual. However, I would say this, that this was not a judicial inquest. You know, in the UK, coroner's inquests are basically of two kinds. There's medically driven ones and there's legally driven ones. The medically driven ones are typically where it isn't expected that there's anything particularly in the nature of evidence that needs to be weighed up. You tend to have a legally administered inquest where that's happened. So I mean, I've been to many inquests which have been presided over by judges because it's been very, very controversial and it's difficult to know where the balance of evidence lies. This inquest, Alan Turing's inquest, was a doctor's inquest. And this particular doctor had a reputation for absolutely hating lawyers. And so, although my father, who was a lawyer himself, turned up on the day after Alan Turing's death, so the one day between the day before the inquest was due to be held, to say, there's a lot more to this than meets the eye, and I would like to find out a bit more about it. And he was strongly advised by the local lawyers in Manchester who knew the lie of the land that this would be a disastrous course to take because this particular coroner hated lawyers, and the result could be that instead of having taken his own life, well, the balance of his mind was disturbed, which is the verdict that everybody wanted. You could have had, in those days, there was a much more aggressive kind of suicide verdict, which would have had the consequence of cancelling things like life insurance policies and so effectively what they were trying to do was get this middle course, which was if the evidence wasn't conclusively going to show it was an accident, which it clearly wasn't in this case, to get this middle course with balance of mind disturbed, the main thing to do was not to upset the coroner. And you know, if they'd actually gone for accident, that would have upset the coroner, and you would have ended up with the completely opposite result from what you wanted, which was the full-on suicide thing with all the legal consequences that would have flowed from that. And that's quite interesting. Again, I didn't know any of that until I'd actually studied the file, which is in the King's College archive, all the correspondence going between my father and the local lawyers and indeed his own memoir of the rather awkward circumstances. So I think the only way you can concoct a conspiracy out of that 2-day thing is to prove that 2 days was extremely unusual. And I have to say, for medically driven inquests, I'm not sure that it is unusual to have an inquest fairly soon after a body has been discovered. So I don't know, but I'm struggling to find a conspiracy on this.
If I might lower the tone.
You're not going to talk about computers, are you? That would
Eric Jacobi or Eric Cumberbatch?
Yes.
Why?
Oh dear. I'm going to struggle to choose between the two of them. You could also mention Ed Stoppard as well. I mean, all three of those actors have put a huge amount of effort into understanding their character. None of them has approached the character lightly. They've all done lots of work, they've done lots of reading up on it, they've talked to people, and they've tried to find something inside themselves that responds to what they've read about Alan Turing. So in terms of quality of acting, I don't think Derek Jacobi or Ed Stoppard or Benedict Cumberbatch can be faulted. I think Derek Jacobi was probably slightly miscast, particularly by the time he did his TV appearance. You remember he did a stage appearance in the early 80s, and then he was reprised for BBC television about 10 years later. By the time he did the TV thing, Derek Jacobi was in his late 50s. Bear in mind, Alan Turing died at age 42, and most of the Breaking the Code plot set 10 years earlier. So Derek was miles too old to be doing the part. Ed Stoppard and Benedict Cumberbatch are better cast in terms of age, and they also, Stoppard's portrayal is more sympathetic. He doesn't stammer particularly, and he's sort of a more approachable, sort of warm human being. Whereas Benedict is more troubled, and he's a bit more nerdy, and he's much harder to get to know. My sense is that, and it's partly the script, by the way, it's not just Cumberbatch's performance, is driven him, I think, slightly over the line. I mean, if you talk to the people who actually work with Alan Turing, they were saying he really wasn't quite as difficult as that. He had his moments, we all do, but really he wasn't, and so asocial that he wouldn't realise when he was being invited out to lunch. It's not that's not fair. And I mean, but the actors have to work with the script they're given, and I have to say, it's a very compelling portrait in Benedict Cumberbatch's case. And in fact, so compelling even that part of when I give talks about Alan Turing, part of what I try and get across to people is that they need to leave the mythology of Alan Turing, which comes with all these dramatisations, outside the door. Those are movies, those are not biographies, those are not documentary, and it's really, really hard because we all carry around our mental picture of historical figures because of the TV and the movies that we've seen, and it's really, really hard to do that. But in his case, I think there is a danger that Benedict Cumberbatch is Alan Turing, and we now have a sort of like an alternative picture of Alan Turing which comes from talking to people and so forth. So I'm afraid that is now the reality, and we have to go to books to find an alternative picture. So it's fine.
Dan. Interested to see the observation about the connection with the Swan family, who are actually local to where I live at one point. Total aside, Swan tried many types of fibre to create the carbonised filament for his lamp. And the ones that didn't work were then crocheted into antimacassars and doilies by his wife and daughters.
I didn't know that.
Thank you. A computer-related question on his history.
Good, that's one I can throw back at the audience. That's fantastic.
he produced the comprehensive design of the Pilot ACE in 6 or 7 months after he joined NPL. Did he have time to work on it before he joined NPL, do you think? What was he doing in the 6 months or a year before that?
Again,
September 45,
yeah, that's absolutely right. And I think it's a similar story to the design of the bomb. I think it's difficult to imagine that it could all have been done quite so quickly. But and so there's a question about what were the influences on it. But I think, and again, I have to defer to the professional knowledge that's far superior to mine on this. But I think the consensus seems to be that a very powerful influence on the ACE design was John von Neumann's famous paper, what's it called, a draft report on the NVAC, which Alan Turing had seen. He'd seen one of the rare typescripts of it, and he'd been allowed to keep it and study it for a while. So, and I think that, I mean, he probably absorbed the theoretical ideas in that very quickly, and that, I'm sure, was a powerful influence. But I suspect he had already been thinking about it. I think it's inconceivable that with all that work going on around the Colossus lab at Bletchley Park, they were talking about programming computers. They were talking about it in the pub. This is what they were all going to go off and do after the war. So it's quite clear that there had been some sort of the intellectual equivalent of primordial soup going on there, with people sort of chucking ideas in and talking about stuff. I mean, one of the things that's really quite extraordinary, Tommy Flowers is on record as having said this, that on the days when Colossus was not actually doing its properly appointed job, the mathematicians wanted to go around the back and get the damn thing to do long multiplication, which was kind of annoying for the code breakers. But you know, they were actually playing with its capabilities at the time. You know, and so it seems to me that there's all that going on. They're all thinking about how it might be done. But then you put the von Neumann paper into it, which just provides a little bit of intellectual framework, a bit of rigour around it, and then ping, it only takes 3 months to produce the ACE design. But I think the thing about the ACE design is it's quite interesting because it goes back to this whole thing about Alan Turing being a hands-on kind of guy. And von Neumann's paper doesn't mention any hardware in it. It's basically about system design, and Alan Turing's paper is about how you make a machine. You know, and what are the, if we're going to be stuck with this terrible problem of delay lines, how are we going to fix that? So we need to fix that with elegant programming. So he writes about elegant programming. You know, so it's really sort of, it's taken the von Neumann architecture and it's actually developed it into something that's practical. So, but sorry, it's a very long answer to your question, and everybody here knows far more than I do about it, so I should definitely shut up.
There is slightly supporting evidence for that argument from Wilkes, who led the EDSAC team at Cambridge. He read the same paper, he had the privilege of going to the Princeton conference and talking to von Neumann. He asserts he designed most of EDSAC on the journey back on the Queen Mary and arrived back at the Cambridge laboratory ready to engage a team of engineers. It took him about 3 years to get from sketches on napkins or whatever they were to the functional machine. Those early machines were actually fairly simplistic, and once your eye had been opened by von Neumann's system design, if you had appropriate electronics, in Wilkes' case it was counting and subtracting from radar systems, in Turing's case it was from the code breaking. It was obvious, I think, how to apply those ideas to animate von Neumann's concept. And so I think the design phase could have been quite quick for Turing and the ACE machine, but then the implementation took time because making the circuits actually work.
I think you're challenge. I think you're probably right. I think the challenge for Turing was actually involved the typewriter rather than the thinking.
You mentioned the voice scrambler.
Yes.
I think he spent up to 2 years at Hounslow Park developing that. Can you shed any more light on it?
I can. I think without wanting to be disrespectful to the Delila rebuild team, I think that's a myth. I've never believed that Alan Turing spent 2 years with a soldering iron doing something that he was poorly equipped to do. So part of my mission was actually to find out what the truth was for those 2 years, well, 2.5 years, between coming back from the US in early 1943 and the end of the war. Frankly, Alan Turing would be the last person you would let near an engineering laboratory unless you wanted to cause a fire. And talking to the people that he worked with there, so Don Bailey, who's still alive, who was Alan Turing's assistant, that's a misnomer, but that's a technical word for it, at Hounslow Park, corroborates the complete uselessness of Alan Turing in an engineering laboratory. And basically, I mean, it was a great thing. Once Robin Gandy and Don Bailey had been appointed to work with Alan Turing at Hounslow Park, that meant that they could safely kick him out and get on with the sort of the technical job themselves. That said, there was a theoretical piece that definitely was needed for the Delila project, and Alan Turing needed to be constantly involved in that and involved in the report writing and so forth. So it wasn't that he wasn't involved, it's just that it wasn't his full-time job. So you then have to ask yourself, which I've been doing for years, well, what actually was his job? And so I think this is where last year's documentation releases from GCHQ actually become quite helpful, because they cast light into this sort of security role that he had, where there was lots of machinery coming out the whole time that needed to be vetted, and there were ideas that needed to be vetted. There was this Bletchley Park machine group. That's what he was filling his life with. It was a sort of multifaceted role, but the Delila piece was part of it, but it wasn't all of it. I think the problem is that until very recently we've only known about the Delila piece, and so it's been sort of tempting to think that that was all of it. But it's just fundamentally not credible that you put Alan Turing in a laboratory with a soldering iron for 2.5 years without causing World War III. You know, just all the good work on Enigma could have been undone. So I mean, they actually did find a sensible role for him, and the development of Delila was part of it. The development of British encryption techniques was another part of it. So I mean, it's all quite interesting. There's not a lot of documentation about this, but there's now about twice as much as there was, which is enough to just fill out the picture a little bit more.
So, and going back to actually some comments from the previous question about how difficult it was to build something from scratch. But I think it's, as you said, is the kind of primordial soup. Because around about the same time, in the late 40s and 50s, Trevor Pearce had come over from Australia. He went round to East States and Cambridge, and then went back and built Sierra. So on his own, as it were, with all of his engineers.
The thing that comes across as being very interesting from studying this period is how much there was going on in the way of international conferences, and international travel can't be very easy in the immediate sort of 5 years immediately after the war. And I mean, just to take one example, when I'm struggling to remember which group of Americans it was. There was a group of Americans that had a computing conference on the East Coast in about 1948, 49. They had 100 and something people attending this conference. They only had one foreigner, and that was Alan Turing. You know, it was really, really hard for people to get to these things. But it's quite astonishing. Everybody wanted to have these conferences. They wanted to share ideas. It was very much more collegiate and less commercial than it became sort of 40 years later. There's a gentleman in the third row who's been waiting extremely patiently.
Yes, you've said several things about the origins of the bomb, and specifically in the period from mid-39 to 40, when obviously there was work that Turing would have been involved with the BTM group at Letchworth. Is there any evidence that he actually visited the engineers and cooperated with them, or did they just take his ideas and then he returned?
Again, probably John Harper would know much more than me about that, but it seems to me inconceivable that Alan Turing could have explained his ideas without having face-to-face meetings, and many of them, with Doc Keane and the other Letchworth guys. It was a really difficult engineering challenge to create the bomb, partly because the sort of idea of designing a sort of programmable piece wasn't going to be particularly straightforward, but partly because the machine had to stop whenever you've got this sort of complicated thing when you've got 26 wires in the cable, and then what it's looking for is a case where only one of them is live, or only one of them is not live, and those are the two cases you're looking for, and all the others have to be discarded. That's not exactly the way that they ended up designing it, but the engineering challenge of trying to do that thing where you're looking at basically a negative image of the thing that, and both the exact negative image and the positive image are okay, and anything else won't do. So that was really difficult challenge for the engineers at the time, and just to explain that idea is just, it's easy for us who've sort of been sitting there for sort of years poring over it to sort of just explain it in one sentence like that, but get that concept across for the first time must have been very, very difficult. But
yes, well, that must have been done well before Christmas.
I think that's right, but I have to say I haven't personally found any documentation around that era which actually sort of does anything at a sort of a technical engineering level in terms of to and fro.
The parts were being made at Letchworth in November of 79.
Speculation. Yes, I mean I don't know the answer. Talk to John, who's in the row in front of you.
I mean, just one snippet. We have got engineering drawings that are dated only 2 days after the outbreak of war, and that is the time that Alan Turing was supposed to have got first involved.
Yes, which clearly gives the lie to the sort of imitation game model that in the nick of time, blah blah. But Alan Turing first started working on the Enigma problem. Certainly no later than January 1939, and in my opinion as early as September 1938. There is very weak evidence that he might have been involved even earlier than that, but it's very weak and I just can't personally put a great deal of weight on it. But I think that he was approached by the recruitment team for Bletchley Park in the summer vacation 1937, along with a bunch of other fellows of King's College, Cambridge, and very rapidly after his recruitment he was assigned to working on Enigma and was having meetings with Dilly Knox at Dilly Knox's home to talk about Enigma and what the problems were and the progress they made on the unsteckered Enigma during the Spanish Civil War and so forth. So he knew about the problem. Where I find it hard to believe that vast progress was made is the immense leap forward after the meeting with the Poles in July 1939. Now that does give us enough time for Knox to come back from that meeting in July 1939, have shared his thoughts with Turing, which we know he did. There's documentary evidence that he shared his thoughts with Turing immediately after that meeting. And there's still enough time for Alan Turing to have come up with the fundamental ideas for the bomb in time for John's blueprints to have come out. But I'd quite like to know what the blueprints are that you're talking about, so we should have a chat about that, please. Because we know that the Poles shared their own technology for their own bomber machine in the July 1939 meeting, and any mechanical attack on Enigma was going to need the manufacture of rotors that were mimicking the rotors in the Enigma machine. That's how the Polish bomber worked. It's how Alan Turing's bomb worked. So we know that there was going to be a whole load of effectively components that were going to be needed for a mechanical attack anyway, regardless of what the ultimate shape of the machine turned out to be. But what those blueprints actually are about, we should talk about.
Okay, one final question, Simon.
Thank you. Thank you for a very interesting talk. There's one minor point that perhaps we should talk about later. you said that the Manchester machines were built from leftovers of Colossus. I think it's not true. So
you're the man who's going to correct me on this one.
I think in a pub afterwards
well, I couldn't be corrected by anybody more eminent. You will also see that I shamelessly stole a picture from your book for the thing about how did this happen, which.
Thank you very much. Thank you very much again. And thank you for the questions and answers. Thank you for your questions, and thank you very much indeed, Sir Dermot, for your answers. So we've had a wonderful time listening to your presentation and your responses to the questions. So thank you.